discuss about the mathematical models only. So ultimately the mathematical models are of two types. Second one is the stochastic. Yeah. So stochastic means when we are considering the randomness, like if we are considering the growth of the population, so this growth of the randomly at a moment of time, like by the earthquake, right? So the earthquake is how the population will. So here we need to stochastic. Here the left side, here we have some kind of continuous. So for the differential equation, three-type continuous differential equation are again two types, like autonomous and non-autonomous. So autonomous and non-autonomous means, like in the differential equation system, dx over dt is equal to fxt. So if this fx is dependent on time, right, then this is known as the non-autonomous system. Otherwise, this will be autonomous. So if the t disappears in fx t, then it is autonomous case. Otherwise, we have to consider the non-autonomous case, and all the discrete, continuous, autonomous or non-autonomous are of the linear or non-linear type. So linear type, that means if the derivative is the degree of the derivative or the dependent variable is 1, or there is no product of the dependent variable and its derivative. So this is the case of the linear differential equation. So here the system or maybe the non-linear differential equation. So ultimately this is dependent on the situation which we will consider, right? So these are some terminologies which can be very much useful in the developing of the mathematical model. So the first one is the phase space. So simply phase space means if suppose we are considering two-dimensional system, and x and y are two variables which represent a particular state. So the graph between this x and y is basically the domain that can consist. The graph between x and y is nothing. This is the phase space, right? So ultimately here you can see. Okay. So ultimately here the first graph basically just represent the phase space, and the next one is the phase plane. So suppose if we have only two-dimensional system, so this phase space will come to phase plane. The phase curve. So phase curve basically the path, or we can say the graph between the state variables x and y. And if we are choosing different initial conditions, then we can have the graphs between x and y. So we have the x and y. So this is known as the phase portrait, right? Now come to the equilibrium point. Here I will actually try to cover these basic concepts in short, right? So that we will try to include some realistic examples. So equilibrium point situations means a situation which does not change with respect to time. So this dx over dt is 0. So by finding the solution of this equation fx is equal to 0, so the value of x is nothing. These are the equilibrium point. So here equilibrium point may be stable, asymptotic is stable, or unstable. So simply asymptotic stable means we are talking about the convergence. Convergence means if the solutions are approaching to the equilibrium point and even enter. So this is the case of asymptotic stability. If the solutions of this system, dx over dt is equal to fx. So if the solution x is approaching to the equilibrium point like x star, or the solution is approaching the neighborhood of a particular x star, so this is known as the stable, right? And if it is divergence or it is diverging, so this is the case of instability. So here the point. So sometimes if we are not able to find the analytic solution, then we can the semi-stable equilibrium point means if it have four types of the equilibrium: node, saddle point, center, and on the basis of the formation of the trajectory. Here we are dividing the equilibrium. We are not and even this is known as node, right? So the equilibrium point may be the node and or unstable. Stable, that means if all the solutions are approaching, then it is stable, otherwise it is unstable. Now come to saddle node, or we can say the saddle point. So in the case of the saddle point, what is happening here? Some solutions are approaching to the equilibrium point and some solutions are moving away from a particular equilibrium point. So if we have this kind of structure, this is an example of saddle point, and saddle point is always unstable, because unstable simply meaning is if at least any solution is diverges from the equilibrium point, so we can say this is unstable. So this saddle point is always unstable. The next one is the center. Center means if we have equilibrium point like x star, and in the neighborhood of star, if we have a infinite number of the closed curve, right? Means this time basically the solutions are oscillating. So if we plot the curve between the state variables, so here we have a closed curve. So if we have infinite number of the closed curve in the neighborhood of the equilibrium point, so this is known as the center, right? Center equilibrium point. So center is not asymptotically stable, because here the curve, or we can say the solution, are not approaching to the equilibrium point. They are approaching just nearest to the equilibrium point, because you can see here what is happening. The radius of the center is reducing, right? But we cannot have of zero radius. So if the zero is the equilibrium point, then we cannot approach to exactly at zero, but we can approach in the neighborhood of the zero, right? The next one is spiral. So if the trajectory is having this kind of the representation spiral, where the trajectories are approaching to the equilibrium point, but in the spiral form, so this is known as a spiral equilibrium point. Now come to two-dimensional system. Suppose we have a problem where the two-dimension, or we can say the two state variables are enough to represent that particular problem. So ultimately we can have this two-dimensional system. And suppose the two-dimensional system is linear. However, in the reality, we don't always have the linear system. But suppose if we have a linear system, dynamics without finding the solution, both the system can convert the differential equation in the form of this df is equal to the column vector which represent x1, x2, and a is the coefficient matrix of the right hand side of the equation. So here from that particular matrix we can find out the eigenvalues, or even we can find out the solutions here. So here x is equal to c1 to the power lambda t, or y is equal to c2 to the power lambda t. This is the analytical solution. And here what is happening? Lambda represent the eigenvalue. So the same eigenvalues we can have through this matrix A, coefficient matrix A. So then this x and y, what will be the value of x and y? If lambda is negative, that means x and y are approaching to 0. The equilibrium point. Ultimately, if values are negative, then the solutions are approaching to 0, 0. So this is the dynamics of the system. Dynamics we can find through that particular criteria or that particular approach. So if we convert the linear system into the form of matrix, so we can find out here the eigenvalues, and for the eigenvalues we need the characteristic equation. So this lambda square minus trace of lambda plus determinant of A is equal to 0. This is the characteristic. So ultimately, one thing is clear. If we want to find out here the eigenvalue, the eigenvalue is dependent on the trace and determinant, right? So if is suppose negative and determinant is positive, so ultimately this equation has two negative roots. Why we are talking about negative only? Because one thing is so the whole theory is related to the negativity of the eigenvalue. But suppose if the eigenvalues are not real, they are complex numbers. So in that particular case, you know, in the case of the complex root, the solution basically is like e to the power real part into t and bracket of something cos and sine. Right? So if the real part is suppose 0, that means e to the power real part into t. Part is negative, then this entire solution is again approaching to 0. So in the case of the complex root, if the real part is negative, to the 0. So here basically we have this is the first for the real and second for the complex. So ultimately the entire nature of this kind of the system is dependent on the nature of the eigenvalues. So yeah. So these are some specific cases, and ultimately the negativity is sufficient for the stability part. Now you can see here. So if the eigenvalues are the real, unequal and of the same sign, so here the equilibrium point will be asymptotically stable. So ultimately this is the theory behind the dynamical system or behind the concept of the stability part. Now this is what? This is actually we can say this is the trace and determinant curve. So squared minus trace of lambda plus determinant of a is equal to 0. This is the quadratic equation, right? Or we can say the characteristic equation. So from this quadratic equation, we can find out the value of lambda, and lambda basically is dependent on the discriminant. And if the discriminant is positive, the root will be real, and if this discriminant is negative, then root will be complex number. So here, if suppose the trace is positive and the determinant is also positive, right? So what is happening? If trace and determinant both are positive, then this delta basically is what? This delta, if we are below of the delta, so we have the complex, the real part is positive, and if we are above of this curve, so ultimately here we have the positive real. And in the case of the positivity, what is happening? The solutions are not approaching to the 0, means equilibrium point are unstable. So if trace is positive, determinant is positive, then the equilibrium point will be unstable. Same in the second quadrant, what is happening? Here the trace is negative, determinant is positive. In the case, if we are talking about the real root, so if we are talking about the complex root, so the real part of the complex root is negative. Where the trace is negative, determinant is positive, equilibrium point is always asymptotically stable. Stable means the solution are approaching to the equilibrium point, right? So this is the entire theory for the two-dimensional differential equation system. Now this is the linearization method. If suppose we don't have the linear system, or we can say if the systems are non-linear, then we can convert these with the help of the method. That means here we can linearize the system point. So this here we try to linearize the system. So ultimately here the coefficient matrix is nothing, that is the Jacobian. So if we have the non-linear system, then we can find out the Jacobian at the find out the eigenvalues. So there is a theorem that is known as the Hartmann and Grubman theorem, and this Hartmann and Grubman theorem is very important because these theorems confirm that the dynamics of the non-linear system are same. However, there may be some differences in the pictorial representations of the solutions, but ultimately the so if you are dealing with the non-linear system or if you are dealing with the linear system, the dynamics of both the systems are same, right? So if we have the non-linear system, then we can try to rewrite the system around the equilibrium definitely one here. There is no need to find out the analytical summation. That means we deals with the equilibrium point and the stability of the equilibrium point. Yeah. So this is the Hartman and Grobman theorem. So here you can see the dynamic. This is the dynamics of the nonlinear system. This is the dynamics of linear one. So you can see here the dynamics is still same. Now there is another method that is known as the Rouse-Hurwitz criteria. So this Rouse-Hurwitz criteria basically is somehow dependent on the Hurwitz determinants. Now come to the Lyapunov direct method. So we also use this method for the stability analysis, either for the means zero equilibrium point or the non-zero equilibrium point. And there are two terms that are the local stability and the global stability. So the main difference between local stability and global stability is local stability is refers to the linear stability. So linear stability means here we are linearizing the nonlinear systems around the equilibrium point. That means we are selecting the initial conditions just near about of the equilibrium point, right? So if we are from the local stability, and if we are choosing the initial condition from anywhere of the domain, so this is the case of the global stability, right? So sometimes it may happen, but it is not global stability. We are choosing the initial condition around of the equilibrium point. If suppose we choose the initial condition arbitrarily from anywhere of the domain, so the stability may be changed, right? So both the local and global the long-term dynamics of the dynamic system. So in this Lyapunov direct method, basically we need to consider a positive definite function, and the derivative of that positive definite function should be negative. So if it is negative, then the equilibrium point is asymptotically stable. This is just one example of the Lyapunov stability. So here we have a system and we have a positive definite function. Then we can find out here the derivative, and of course the derivative is negative if we consider this kind of a domain. So this particular domain, here we have the equilibrium point and also the derivative is negative. So the equilibrium point is asymptotically stable. We skip actually this part. Basically limit cycle. Limit cycle, that means when the state variables are oscillating, that means if they are fluctuating between 2 points, right? So in that particular case, the graph between the variables will be closed. So if we have a closed curve and rest of the trajectories are approaching to this particular closed curve, either outside or from the inside, so this is known as the limit cycle. Sometimes the limit cycle will be stable or stable limit cycle means if the outer trajectories or the inner trajectories are approaching to the boundary of the closed curve. So this is the case of stable cycle. Otherwise, it is known as unstable limit cycle. So this is just one example. Yes. Now these are some conditions for the non-existence of the limit cycle, and also we have some kind of the bifurcation. So bifurcation simply meaning is the structural changes. So if suppose by changing the values of the parameter, number of equilibrium point is changing, right? Or we can say the stability of the equilibrium point is changing. So this is the structural change in the system, and sometimes it is known as the bifurcation, right? So how these mathematical theories is applicable in the case of realistic problem. So now here we are moving to the ecological part, that is known as the mathematical ecology. So these are the two important books. If someone is suppose starting to work, the first one is the Treatment of Mathematical Ecology by the Marquardt, right? The author is Marquardt, and the second book is Mathematical Biology. This is very famous by the J.D. The publisher is right? So what is the mathematical ecology? Okay, what is the ecology? So basically living organisms with the environment. Right? So if we mathematically deal with the same kind of the relationship of the living organisms with the environment, so this is known as the mathematical ecology. Right? So in the ecology, we deal basically with the relationship of living organism. Living organism means it may be insect, it may be animal population, or it may be human population. So if we consider these living organisms and we are trying to find the effect of the environment on the growth of the populations. So this is just one example of the ecology. So the single species model. So in 1798, Thomas Malthus has developed a model for the growth of the population, right? And this model is specifically for bacterial population. So this bacterial population is growing basically in the multiple ways. Means it will be 2 times, then 4 times, 8 times, 16 times. So it is just increasing. So if suppose the growth of the population is increasing, so how to develop a mathematical model? So the simple is here the rate of change of population. Rate of change of population. Suppose population is x times t. So the rate of change basically is dx over dt. So this dx over dt is proportional to the x, whatever the population we have. So as per the proportional population, here the growth will be increased, right? So this dx over dt, or we can say dn over dt, is proportional to n, and if we remove the proportionality sign, so here we can consider a constant. So this r basically is the constant, and this r is the birth minus death, right? So whatever the birth we have, whatever the death we have, so that their difference basically is the growth rate. So this is the Malthus growth model, and from this model we can find out the solution easily. So nt is equal to n0 e to the power rt. This is the solution. Okay, because here we are able to find out the analytical solution, so we can go forward with the analytical solution. So if it tends to infinity, then nt is approaching to infinity, right, in the exponential manner, like this time. So if this r is positive, then this nt approaching to infinity. If r is negative, then nt is approaching to 0, right? So these are the mathematical results. So how these results are related to the biological problems, or whether this model is valid or the model is realistic. So in the reality, can it is possible any population grow up to infinity? The answer is no. No can any population increase up to infinity, or any population can die out, right? Because reality is not possible. So somehow this model is not realistic. So here we need to modify this model. So there is another called Berhart. So P. Berhart basically modified the model by considering another assumptions, and the assumptions is limitation of the food, or we can say the limitation of the resources. So what is happening in the reality, we have actually a limited space or the limited food. So the population can grow as per the limitation of that particular food. So initially, if suppose we have sufficient food, so the growth rate will be high, right? But after certain time, what will happen? The food will decrease. So if the food is decreasing, that means growth is also decreasing. Ultimately, what is happening? The population is growing. If the food is growing, but at a certain moment, when the food is starting to decrease, so the growth rate is also decreasing, right? And after certain moment, it will be saturated. So this kind of assumptions is much more realistic. So if we consider the concept of the limitation of the food, so due to this kind of the limitation, there is a competition between the population for the food, for the space, for the resources. So due to that competition, the growth of the population will be decreased. So that's why here we can include another term in the Malthus growth model. So this dn over dt is equal to Rn is the Malthus growth decay of the population. This Rn square by k. N square means the competition of n with the n. So there is a competition between the same species. And k is the carrying capacity of the environment. Carrying capacity means maximum size of the environment which can hold the maximum size of the population. So under this maximum, there will be a competition between the species. So here the population will decay. So this model is known as the logistic growth model. This is also a single species model. And here in this model, what is happening? Whatever the initial condition is, whatever the initial size of the population, if this initial size of the population n naught is less than the carrying capacity, then the population is approaching to its maximum size, that is k, and after time it will be saturated. And if suppose the initial population is higher than the maximum size, so what will happen? There will be some death of the population due to the limitation of the food. So ultimately this population is approaching to the zero. So the same result can be found either by the analytic solution or by the statistical concept. So these are the very basic mathematical models. Now come to the another model, that is the. So in the ecology, what is happening? Basically we have three types of the interaction. The first interaction is prey-predator interaction. Prey-predator interaction, that means if we have suppose two populations of different level. So what is happening? The top population can attack on the lower population. For example, if we consider the grass is also living organism, or the cattle population. So cattle population can consume the grass for their growth. So this is just an example of the interaction between species. So this kind of interaction is known as the prey-predator interaction. Right? So suppose if we have this kind of problem in the nature, species can attack on another. Right? So how to develop the mathematical model? So this one is the mathematical model. We suppose X represents the prey population and Y represents the predator population. So this predator population can attack on the prey. So ultimately dx over dt is equal to ax. This is the mass of the prey, and the second term minus b. So this xy represent the interaction between x means prey and y means predator. So this represents the interaction between prey and predator, and this minus sign reflect there is a decay in the prey population because the predator is attacking on the prey and consuming it, right? So due to that, here there is a decay in the prey population, and of course due to that, the growth of predator population will increase, and the last term minus of dy will represent the death of the predator population. So this is the prey-predator population. Another kind of the interaction is competition. So the growth of both of the population will increase, right, if there is a competition in the population. And the third one is mutualism. Mutualism means if the growth of both of the population is increasing due to this interaction, so that is mutualism. So for any kind of the interaction, here we can develop the mathematical model of this kind of the initial value problem, and then we can find the equilibrium point, and of course here equilibrium point. Then we can find out here the Jacobian, because the system is non-linear. So the eigenvalues of Jacobian, one eigenvalue basically is positive and other eigenvalue is negative. That means the first equilibrium point 0, 0 is unstable. So here the x and y are not approaching to 0, 0. That means prey and predator are not extinct with respect to time. Whatever the time, here the prey and predator will survive. Now come to the next equilibrium point, that is the non-zero equilibrium point. So at the non-zero equilibrium point, this is a complex eigenvalues whose real part is 0. So if the real is 0, so this is the case of oscillation of the population. That means these x and y are not extinct and they are approaching around of the equilibrium point in the oscillation times, right? So they are approaching to that particular equilibrium point, but they have some kind of point, they have some values above that equilibrium point or the lower of that equilibrium point, right? So even in reality, it is happening. The growth of the population is always oscillatory. So this is just one example that how we can apply this theory to the pre-predator kind of the system. So this is just a validation if we consider some hypothetical values for the parameter. So here what is happening? The second one in the first quadrant, here we have the closed trajectory. So closed trajectory means oscillated systems, and this origin basically is unstable. Now this is the logistic. So if we consider or we replace the exponential growth by the logistic, so we can have here the with the logistic growth. So here with the analysis or by the eigenvalues one set, we find out here the now the next part, that is the epidemiology part, right? So these are two very important books related to the mathematical epidemiology. The first one is the mathematical theory of the epidemics by N.T.J. Bailey. This is famous book. And the second is an introduction to the mathematical epidemiology. So this book basically was published in recently 2009 by the Springer. But both the books are have the enough material if you like to start in this particular field. So what is the mathematical epidemiology? So epidemiology simply means is study of the we are dealing with the diseases kind of the problems, infectious diseases. So ultimately we deal with the epidemiology. If we deal with mathematics, right, means if we consider or if we study these problems through the mathematics, so this is known as the mathematical epidemiology. And why it is means essential. So you can see here for particular diseases, this is the traits of the disease. So even having means lot of technologies, lot of controlling methods, but still we are not able to control the mortality due to the diseases. So day by day this mortality basically is increasing. That means here the different kind of the theory is required so that we can provide some kind of the suggestions or some kind of the theory so that they can control the disease. So ultimately here the disease can be spread through the bacteria, viral, fungal or the parasites. So the disease can be spread in the direct mode. Direct mode, that means from one person to another person, either by direct contact or by the droplets. Now come to the second part. So here the second part is indirect. Indirect means like so we can get infection from that particular places. The second one is the airborne. So if we are having the infection from the through the air, so that is an example of the airborne diseases. And the third one is the fomites. Fomites means like the door handles or the similar kind of the objects. So when we are touching these door handles, so here the virus or the parasites can be transmitted, right? So here the disease can be spread. So these are some method of the disease transmission. And the third one is indirect. Yeah. So indirect means like the example of malaria. So in the case of the malaria, what is happening? The malaria cannot be spread to a person. Another species is like a mosquito. So the mosquito basically can transmit the virus from healthy person to the infected person. Or we can say if this mosquito bites the infected person, so ultimately the virus can be transmitted to the mosquito, and once the mosquito bites the healthy person, so again this virus can be transmitted to the healthy person. So this kind of the transmission of the diseases basically is the indirect transmission. So ultimately here we have three: direct transmission, second is indirect transmission, or the this is the case of the vector. So this is the third one, that is the vector. Or we can say the vector here may be the mosquito or be the flies or any other kind of the animal population. So ultimately here we will try to develop some mathematical model for this vector-borne diseases. So the first one is the SI model. This is very basic. So how to develop here the mathematical model for the disease kind of the problem. So ultimately our main target is to divide the entire population based on their nature. So if suppose the human population is healthy, that means they are susceptible. Susceptible means they are healthy, but if suppose this healthy person is having some kind of the contact with the infectious person, they transmit. So healthy person basically is known as the susceptible, and the person having the disease is known as the infectious person. So we can divide the entire human population into two groups, susceptible and infectious. So if suppose we are dividing the human population into two groups, so the susceptible person may be transmitted when get into contact of the infectious. So this S into I basically is the contact of the susceptible and infectious, and beta is the probability at which these interactions will be successful. So ultimately what is happening, this beta Si basically is moving to the infectious, or we can say the susceptible person with the rate of beta is moving to the infectious compartment. So this is the simple SI mathematical model. Now suppose if we consider another phenomena like the immunity. So what can be recovered with the cell immunity, means there is no need for any kind of the medication. Without medication everyone has the immunity, so due to this immunity the person may be recovered from the disease. Ultimately the infectious person may again move to the susceptible, or may again move to the healthy person, right? So what is happening here, this susceptible person is moving to infectious, and a fraction of the infectious person by the self immunity is again moving to the susceptible. So this model basically is known as the SIS mathematical model. So if suppose you are considering the problem where you are having the concept of the immunity, but this immunity is not permanent. This immunity basically is an immunity, because you are moving to the susceptible, that means you can again get infected, right? So now come to another model, that is SIR model. So SIR model means once you become healthy, so you will never become infected, right? For example, in the case of chickenpox, so if someone is having chickenpox and if he is recovered from that particular disease, so in the entire life span he never again infected with the same diseases. So this is the case if suppose you are dealing with the chickenpox, so you need to develop an SIR mathematical model, right? So in the SIR mathematical model, what is happening, a fraction of the susceptible is moving to the infectious, and a fraction of the infectious person is moving to the recovered. So this is simple SIR mathematical model. Now come to the demography. Demography means if we are considering the birth and the death. So if this capital lambda basically the birth. So whenever we have the new offsprings or the new populations, so basically new populations is always healthy. We can consider the new population is always healthy. So here with the rate of the lambda, this susceptible population is growing, and again we have the similar kind of the behavior, and every population, either the susceptible, infectious or the recovered, is dying with the same rate. So this is the natural death rate. So if we consider the demography concept, so here this SIR model can be modified in this form. And now come to the analysis part. So same here we can apply the concept of the equilibrium point and the stability of the equilibrium point. So ultimately what is happening, we can non-dimensionalize the system because we have the number of parameters in the system here. So to reduce the parameter, here we can okay. So this is just example of the SIR model with the demography. Now so if this is SEIR model, so here we are considering the exposed compartment. Exposed point means sometimes what is happening here, is already having some kind of infection, but the symptoms is not showing, or we can say this person is having the disease but not able to transmit disease to the other person, right? So on the basis of that kind of assumption, we can consider IR mathematical model. So this is the local stability, global stability. With the help of the Lyapunov method, here we can find the global stability. And now moving to the next mathematical model, and after this we will finish. This is the next generation approach method for the basic reproduction number, and of course you for the basic reproduction number. So basic reproduction number is also playing an important role in the controlling of the disease. Yeah, this is vector-borne disease model. Just a moment. Since we have actually okay, so basically here we will consider one example. We can skip all these guys. Yes. So now this is just one example related to the dengue transmission, right? And after this model, we will close actually this lecture. So ultimately, this is the mechanism of the dengue transmission, and you know the dengue transmission can be transmitted, or here the person can be infected by the dengue disease with the four kind of these serotypes: the dengue 1, dengue 2, dengue 3, and dengue 4. So ultimately, what is happening? Two kind of the infection. The first infection is the primary, and the second infection is the secondary infection. So the primary infection can be caused either in the children or in the adult population. So in the children, basically it is transmitted by the dengue 1, dengue 3, and dengue 4, and the this is happening basically in the children after the age of 15 years, and after the 15 we can consider here the adult population. So saying the adult population and the primary infection by the same kind of these serotypes. Now come to the secondary infection. So secondary infection is mainly happening in the children due to the dengue viruses, right? So this is the mechanism of the dengue transmission. So what is happening here? Here we can consider the human population, and based on the previous means literature, here we can divide the human population into some groups. But ultimately, this disease is spreading between two kind of the populations that is dependent on the age. That means here the disease is spreading in the children as well as in the adult population. So we can divide the human population into two different classes: the one for the children and other for the adult. Right? So here we are considering the concept of the stage structure. So ultimately, this S1, I2, these three are the immature population. Immature population means children. So here the children can have I1 primary infection or I2 the secondary infection, and this A basically is the adult population. So adult population can have only the primary infection by the dengue 1, 3, and 4. So ultimately, what is happening here? U and V are the density of the vector population. Just 5 minutes. So here U and V are the densities of the vector population. So ultimately, how the disease is spreading? So this lambda is the growth of the children population, and here mu1 and this P2 basically are the decay of the I1 and I2 population. So what is happening here? This V means infected vectors, or we can say the infected mosquito. So when this infected mosquito bites the susceptible children, so that means the viruses can be transmitted from vector to the children population. Now this S basically is moving to A. That means the fraction of the children population becomes adult. So here the N fraction of the susceptible population becomes adult, and then this V means infected vector can bite this adult adult population. So adult population can have the primary infection, right? So this adult population is basically moving to the infectious compartment, and then infectious compartment is moving to the recovered compartment. And now what is happening is I1 is moving to R. That means the children having infection can be recovered either by the medication or by the self immunity. And again I2 is also moving to R, means the children having secondary infection can also be recovered. Yeah. So ultimately here this U can be interact with I1 and I. I1 and I means infected human population. So when this susceptible or healthy mosquito bite the infected, so this susceptible mosquito can again become infectious, right? So this is the entire transmission of the diseases between the children and the human population. And here what is happening? We are means harvesting this U and V with the rate of P and Q, because what is happening in the case of the dengue, we basically try to kill out a portion of the mosquito either by the chemical spraying within the environments or by means elimination of the larva of the mosquito. So this is the dengue, or we can say the mechanism of the dengue transmission. So ultimately here we have a higher dimensional mathematical model, and of course we cannot solve or we cannot find here a mathematical solution for this particular mathematical model. So here we can find the equilibrium point, we can find here the long-term traits, right? So the similar kind of mathematical theory we can apply here to find out the dynamics. So this is just the one example that how the stability theory can be applied for the complex ecological or the epidemiological problem, and how we can suggest a means some kind of theory for the policy decision making, right? So up to here I am stopping. So if you have any questions, then really I will be very happy to answer.
Consider the continuous models. If you have any doubts, you can ask. Otherwise, just we can congratulate him for his nice lectures and nice presentations.
Thank you very much for the organizers, and especially for the Dr. Prasad, Dr. Manish for providing me this opportunity. So really, I am very happy to interact with you, and thank you once again. Thank you to all.
Thank you to all of you for my and thank you for providing me the opportunity as a chair. So thank you. We are required. Please welcome on the desk. We need 20 minutes. We have a very limited time. Most of the presentation is not yet started. 10-15 minutes. I request to welcome Nitish Rajpuri sir by 20 minutes. Yes.
Professor. You will continue. Sorry, Mr. Professor, to welcome Professor Dina sir.
Sir.
I welcome all for the next section by Dr. Sumit. He is a researcher and current data department for mathematics at Indira Gandhi National Tribal Central Institute for Mental Madhya Pradesh. He has PhD from Gurukul University. His expertise are in eight areas of mathematics, including loading optimization, data enrollment analysis, soft computing, performance analysis, cryptography, etc. He has published research in journals which are indexed in Scopus and Web of Science, and he presented his research in several national international conferences, and he has delivered invited talks at prestigious institutes like JNU and South Asian University. Till date, 4 students have been awarded PhD under his guidance, and 7 PhD dissertations he has guided, and he has received or filed 7 patents on mathematical and computational devices. He has received prestigious awards including Rajiv Gandhi National Fellowship in 2011 and Outstanding Patent Accomplishment in 2025. I request Professor Sumit Dina to start his presentation.
Thank you. So thank you so much प्रशांत जी और सबको धन्यवाद। और स्ट्रेंथ बहुत कम है इसलिए उतना खुश नहीं हूँ मैं, उतना दूर से आया हूँ, लेकिन स्ट्रेंथ होना चाहिए। चलिए अब जो है सो मेंटेन करेंगे। सो पर ये बताइए जो भी पार्टिसिपेंट बैठे हैं वो कौन से स्ट्रीम के हैं? फिजिक्स, मैथमेटिक्स, सिविल मैथमेटिक्स के हैं? सब अदर सब्जेक्ट ऑल्सो। फिजिक्स के भी कोई है क्या? फिजिक्स के भी नहीं है, ठीक है, कोई नहीं। अच्छा मैडम स्टार्ट करते हैं। अच्छा आगे चेक करने के लिए
Pointer is there
Pointers.
on the table.
ओके ये ना so having quantum supremacy and the transformation of data intelligence, this is the topic. So are you comfortable in Hindi? हिंदी चलेगा? चलेगा, good. देखिए ये जो क्वांटम सुप्रीमेसी है एंड द ट्रांसफॉर्मेशन ऑफ डेटा इंटेलिजेंस, ये क्या है? इमर्जिंग टॉपिक है। आजकल इसके ऊपर ज्यादा रिसर्च हो रहा है और डेटा साइंस है, मशीन लर्निंग है, एआई है और कंप्यूटिंग है। तो आप लोग कहीं ना कहीं नाम सुने होंगे क्वांटम कंप्यूटिंग के बारे में, तो जानने की कोशिश की होंगे ये क्या है बोल के। तो रिसेंटली मैंने फैकल्टी डेवलपमेंट प्रोग्राम न्यू दिल्ली में साइंटिस्ट लोगों के साथ मैंने वो 2 दिन अपना ऑफलाइन टॉक दिया था। तो चलिए अब मैं आपके बारे में समझाता हूँ कि क्वांटम कंप्यूटिंग है क्या। तो फर्स्ट डेफिनेशन कम्स फ्रॉम द ड्युअलिटी। लाइट इज ए वेव और लाइट इज ए पार्टिकल। लाइट वेव है या लाइट पार्टिकल है, एक सबसे बड़ा क्वेश्चन साइंटिस्ट के विषय में। बहुत सारे लोग साइंटिस्ट जानना चाहते कहते थे कि लाइट इज ए पार्टिकल और लाइट इज ए वेव, क्योंकि कुछ साइंटिस्ट को लगता था कि लाइट पार्टिकल है और कुछ साइंटिस्ट को लगता था कि लाइट एक वेव है। तो उसके बाद एक एक्सपेरिमेंट किया गया, इस एक्सपेरिमेंट्स में यह साबित हुआ कि लाइट इज ए ड्यूअलिटी, समटाइम इट बिहेव लाइक ए पार्टिकल एंड समटाइम इट बिहेव लाइक ए वेव। तो उससे यह साबित हुआ कि जो साइंटिस्ट का जो दुविधा था कि लाइट इज मेड अप ऑफ ए पार्टिकल और लाइट इज मेड अप ऑफ ए वेव, तो उससे यह निष्कर्ष निकला कि लाइट इज पार्टिकल एंड लाइट इज ए वेव। मतलब एक ही चीज दो कैसे हो सकता है, एक ही चीज दो कैसे हो सकता है। आप अपने इंटरमीडिएट में फिजिक्स पढ़े होंगे, फिजिक्स में यंग सबसेट एक्सपेरिमेंट पढ़े होंगे, सुने तो होंगे ना, तो उसमें पता चलेगा। तो ये जीरो से स्टार्ट कहा होगा क्वांटम कंप्यूटिंग। क्वांटम कंप्यूटिंग कैसे इंट्रोड्यूस हुआ, साइंटिस्ट के दिमाग में आइडिया आया कहां से, इसके बारे में मैं स्टोरी से समझा रहा हूं। अभी क्वांटम कंप्यूटिंग का जन्म नहीं हुआ, अभी साइंटिस्ट का डिस्कशन चल रहा है। तो ये बात साबित हुआ कि लाइट इज मेड अप ऑफ आगे पीछे हो रहा है, थोड़ा करेक्ट नहीं आ रहा है, स्लाइड्स एंटर मारना पड़ेगा लगता है, ऐसे बोले तो फिर मजा नहीं आएगा। पीडीएफ नहीं मैडम, अगर ये करता हूँ तो ये होता है, तो नेक्स्ट बार बटन बता दीजिए। हाँ ये देखिए ऐसा करता हूँ ना, नेक्स्ट कैसे करना चाहिए, नहीं तो एंटर दबा के मैं लूँ क्या, यहाँ पे रख दीजिए, मैं एंटर मारते जाऊंगा। अब बैठिए, मैं नेक्स्ट बोलते जाऊंगा तो पता चल जाएगा, ठीक है। नेक्स्ट नेक्स्ट स्क्रीन लो, स्क्रॉल डाउन करो, हाँ वो स्लाइड्स। सो यहाँ पे देखिए एक्सपेरिमेंट चल रहा है, यंग डबल स्लिट एक्सपेरिमेंट इज गोइंग ऑन। जो वो इमेज है वो इट इज नथिंग बट इट इज एन ऑब्जर्वर। ऑब्जर्वर मतलब कोई इंसान नहीं है, मतलब एक इंस्ट्रूमेंट समझिए। मान लीजिए यहाँ पे एक यंग डबल स्लिट एक्सपेरिमेंट चल रहा है। अब जब चल रहा है तो एक क्या हो गया, मैंने पिछला साइड सेट किया, वो पार्टिकल नीचे बताया, और कैसे वो नेचर बता रहा है, वेव नेचर। ये कैसे हुआ, मतलब वर्किंग है। हाँ अब देखिए, मान लीजिए एक ऑब्जर्वर इंस्ट्रूमेंट है। अब जैसे मैं आके यहाँ पे उसको रख रहा हूँ, तो इतना यहाँ से यहाँ तक आने में एक एयर मीडियम है। उस माइन्यूट एयर मीडियम में इलेक्ट्रॉन अपना चेंज कर रहा है। इतना माइन्यूट एरर में पार्टिकल नेचर सडनली इज कन्वर्टेड इनटू वेव नेचर। मतलब मैं ऑब्जर्वर, ये ऑब्जर्वर है समझिए, इंस्ट्रूमेंट है। यहाँ पे एक्सपेरिमेंट चल रहा है, मैं यहाँ पे रखूंगा और फिर बाहर जाऊंगा। मैं आने से बाहर जाने से जो एयर में डिस्टर्बेंस हो रहा है, उस डिस्टर्बेंस से इलेक्ट्रॉन अपना पार्टिकल नेचर से वेव नेचर हो रहा है। लेकिन उन्होंने ये किया कि जब मान लीजिए कि क्या हुआ, हाँ मान लीजिए कि एक एक्सपेरिमेंट चल रहा है, तब इनको पता चला कि जो आपको देखिए एक्सपेरिमेंट करते हैं, न्यूटन फर्स्ट लॉ, न्यूटन सेकंड लॉ, न्यूटन थर्ड लॉ, ये सब क्या है क्लासिकल मैकेनिक्स में आता है, जो आपको देखते हुए एक्सपेरिमेंट करते हैं। क्वांटम मैकेनिक्स मींस इट इज अ माइक्रोस्कोपिक लेवल, जो हम बोलते हैं मैकेनिक्स। तो ये दो डिफरेंस है। तो एक रिजल्ट निकला, फर्स्ट रिजल्ट क्या निकला, लाइट बिहेव लाइक ए पार्टिकल एंड लाइट इज बिहेव लाइक ए वेव। तो उसके बाद आइंस्टीन ने एक फोटो इलेक्ट्रिक इफेक्ट के ऊपर एक्सपेरिमेंट किया, नोबेल प्राइज मिला, दैट इज कॉल्ड फोटो इलेक्ट्रिक इफेक्ट। उन्होंने बोला कि लाइट इज ए पैकेट ऑफ एनर्जी कॉल्ड फोटोन, इट इज ए पैकेट ऑफ एनर्जी, when electron absorbs the energy it comes to the excited level, and when it comes to the when it loses the energy it comes to the ground state। फिजिक्स में आप पढ़े होंगे फोटो इलेक्ट्रिक डेफिनेशन क्या है, the emission of electrons from a metallic surface when exposed to a suitable frequency called threshold frequency, the emitted electrons are called photoelectrons and the total phenomenon is called a photoelectric effect। मतलब क्वांटम कंप्यूटिंग के लिए आपका फिजिक्स नॉलेज होना जरूरी है, मैथमेटिक्स होना जरूरी है, स्टैटिस्टिक्स होना जरूरी है, कंप्यूटर भी होना जरूरी है। इट इज ए मल्टीडिसिप्लिनरी। तो उनका भी ये मानना था कि लाइट इज ए पैकेट ऑफ एनर्जी। तब उनके बाद नेक्स्ट एक्सपेरिमेंट किया गया, डेविडसन जर्मन एक्सपेरिमेंट, वहां पे भी लाइट इज बिहेव लाइक ए ड्यूअल पार्टिकल। इन क्लासिकल मैकेनिक्स पार्टिकल पोजीशन एंड मोमेंटम इज डिफाइंड। मतलब जब हम अगर मास है तो मोमेंटम है, जब हम देख रहे हैं आंखों से कुछ चीजों को देख रहे हैं तो उसका मास है, अगर मास है तो मोमेंटम है। इन क्वांटम मैकेनिक्स पार्टिकल शो वेव नेचर कॉल्ड वेव मैटर वेव, दैट इज particle has a two type of behavior, it is more prominent when particle has in less in size। मतलब quantum mechanics में there is no mass but there is momentum possible, mass नहीं है फिर momentum है, मतलब mass इतने negligible है कि we can't say। मतलब इनका कहना ये है कि mass अगर ज्यादा रहेगा तो wave proportion कम होगा। अगर मैं यहाँ पे चल रहा हूँ तो कंसीडर मी लाइक ए पार्टिकल, मेरे साथ जो है वो नेग्लिजिबल होगा। जैसे जैसे मास छोटा होता जाएगा, कम होता जाएगा, तब वेव नेचर ज्यादा होता जाएगा। ठीक है, जैसे कि आप एक स्टोन फेंकोगे वाटर में तो वेव्स के जैसे स्प्रिंकल आता जाएगा। जैसे कि आप बारिश में देखते हो लाइट के ऊपर भी थोड़ा सकता है। आर यू गेटिंग माय पॉइंट? सो ये क्या होगा कि मतलब मैं चल रहा हूं, मतलब मैं भी पार्टिकल, लेकिन मेरे साथ जो एसोसिएट हुए हो वो नेग्लिजिबल है। लेकिन जब छोटे स्तर पे आते हैं हम माइन्यूट पार्टिकल, देन इट इज वेरी डिफिकल्ट टू फाइंड द पोजीशन, टू फाइंड द ये। तो यहां पे क्या है, डेल्टा x क्या है, पोजीशन है, डेल्टा p क्या है, मोमेंटम है, इज ग्रेटर देन और इक्वल टू h डिवाइडेड बाय 4 पाई। दिस इज कॉल्ड हाइजेनबर्ग अनसर्टेनिटी प्रिंसिपल। इसके बाद मैं इस डिटेल्स इक्वेशंस में नहीं जाऊंगा क्योंकि मेरे को कंप्लीट भी करना है। अब इसके बाद मैं आता हूं क्लासिकल कंप्यूटर, थोड़ा स्क्रॉल कर लो, आगे छोड़ा। देखिए क्लासिकल कंप्यूटर मींस व्हाट, जो आप कंप्यूटर यूज करते हैं, जो आप फोन करते हैं, उसमें चिप सीपीयू, वो कंप्यूटर काम कैसे करता है, 0 1 बिट्स। ओके, इट इज मेड अप ऑफ बिलियंस ऑफ ट्रांजिस्टर इन सिलिकॉन चिप, बिलियंस ऑफ ट्रांजिस्टर्स। ट्रांजिस्टर का मतलब क्या है, मान लीजिए एक ट्रांजिस्टर है, अगर ये ऐसा हो गया तो इलेक्ट्रॉन जाएगा ऑन, अगर वो गेट बंद करेगा तो ऑफ। ऑन ऑफ हम क्या करेंगे, 1 0 1 0। तो इस तरीके से देखिए 2 ऊपर नहीं आगे आगे लो। हाँ कैरेक्टर देखिए 8 को अगर हमको सेव करना है तो कितना बिट्स चाहिए, 0 0 1 1 0 0 0। तो कंप्यूटर खाली ऑन ऑफ समान समझेगा। अगर मेरे को 12 स्टोर करना है तो 12 डिस्प्ले में आएगा ना, तो उसके लिए क्या चाहिए, 0 0 1 1 0 0 1 0 0 1 1 0 0 1 0। अगर ए को सेव करना है तो बिट्स लगेगा। लेकिन मिली सेकेंड उससे और थोड़ा सेकेंड उसको 1000 के ऊपर डिवाइड करो, उस सेकेंड को महसूस नहीं कर सकते। उस सेकेंड में क्या हम स्टेशनरी जो इलेक्ट्रॉन रिवॉल्व हो रहा है उसका स्पीड इतना है कि बहुत स्पीड है, वो सभी पोजीशन पे प्रेजेंट है। तो मान लीजिए वो सभी पोजीशन पे प्रेजेंट है, तो वी कॉल इट एज सुपरपोजिशन। इलेक्ट्रॉन रिवॉल्व कर रहा है ना, वो ऊपर भी है और एट टाइम नीचे भी है, ऊपर भी है एट टाइम नीचे भी है। ऊपर है तो 1, नीचे है तो 0, ऊपर इलेक्ट्रॉन है तो 1, नीचे है तो 0। अगर कुछ डिस्टर्बेंस है तो कोलैप्स हो जाएगा, या तो ऊपर या तो नीचे, या तो दाएं या तो बाएं। इसको भी अब 1 या 0, अगर इस तरह से भी 1 या 0, लेंथ तो सेम होगा ना डायमीटर में। राउंड है तो उसका लेंथ तो डायमीटर में तो लेस सेम होगा ना। इसका मतलब क्या है, इफ द इलेक्ट्रॉन इज इन सुपरपोजिशन, माइन्यूट एरर कम्स, इट कोलैप्स इन सुपरपोजिशन। या तो वो 0 पे होगा या तो 1 पे होगा। मतलब अगर इलेक्ट्रॉन इट इज इन सुपरपोजिशन तो हमको एट ए टाइम 0 भी मिल रहा है और 1 भी मिल रहा है। दिस इज कॉल्ड द प्रिंसिपल ऑफ सुपरपोजिशन। नेक्स्ट अब देखिए नेक्स्ट, हाँ 1 बाइट इक्वल टू 8 बिट्स, 1 बाइट इक्वल टू, अब नेक्स्ट अब देखिए 1 जीबी में इतने सारे बिट्स होते हैं, मतलब लगभग 8.5 करोड़ बिट्स, लगभग 8.5 करोड़ बिट्स होता है 1 जीबी। जैसे कि आप मोबाइल यूज करते हैं ना, उसमें इतने सारे बिट्स चाहिए। नेक्स्ट अब देखिए बिट्स, दिस इज क्यूबिट्स। व्हाट डू यू मीन बाय क्यूबिट्स? क्यू मतलब क्वांटम बिट्स, बिट्स मतलब सिंपल जो आप कंप्यूटर में यूज कर रहे हैं, क्यूबिट्स मतलब क्वांटम बिट्स। ओके, हाँ, और अभी मैं आपको खाली बेसिक समझाऊंगा। ये डायग्राम है नेक्स्ट, क्योंकि मेरे यहाँ पे देखिए वो जो फंक्शन वो सुपरपोजिशन पे है, जैसे कोई मेजरमेंट करने आएगा तो कोलैप्स हो जाएगा। इट इज वन टाइप ऑफ ज्योमेट्रिकल डायग्राम। ओके नेक्स्ट, हाँ अब 2 क्यूबिट में पॉसिबल क्या क्या है? 2 क्यूबिट इफ इट इज इन सुपरपोजिशन 1 1 0 0 1 0 0 1। नेक्स्ट, if qubits are in 3, then this much bits possibility will be there. Next, if qubits are 4, again, so what is happening? बस exponentially it is increasing, मतलब multiple हो रहा है। जैसे फिजिक्स में देखते होंगे ना न्यूक्लियर फिशन बोलो तो जैसे चेन रिएक्शन से 1 से 2 2 से 3 जैसे जैसे बढ़ते जाता है ना, उस तरीके से बिट्स इंक्रीज हो रहा है। नेक्स्ट, अब नेक्स्ट, हाँ अब देखिए टूट नीचे, हाँ देखिए मान लीजिए इतने क्यूबिट्स है, तो हमारे पास इतने बिट्स का कॉम्बिनेशन बनेगा। देखिए 2 बिट्स बनेगा। नेक्स्ट, ये आईबीएम का कंप्यूटर है, इसको सुमित बोलते हैं। हाँ दिस इज एंटेंगलमेंट। व्हाट डू यू मीन बाय एंटेंगलमेंट? 2023 में एंटेंगलमेंट के ऊपर नोबेल प्राइज मिला। मान लीजिए ये एक 2 क्यूबिट है, ये यूनिवर्स में है, और ये क्यूबिट है दूसरा यूनिवर्स में है, ये भी सुपरपोजिशन में है। जैसे इसका सुपरपोजिशन कोलैप्स हो गया, अगर इसका 1 है तो उसका ऑटोमेटिक 0 होगा, अगर उसका 0 है तो ऑटोमेटिक इसका 1 होगा। ये साइंटिफिकली प्रूव किया गया। मतलब 2 क्यूबिट्स अगर एक दूसरे से कम्युनिकेटेड है, सुपरपोजिशन में है, अगर उसका सुपरपोजिशन कोलैप्स हुआ, अगर वो एक ऑटोमेटिक सुपरपोजिशन कोलैप्स होगा। मतलब ये स्पीड ऑफ लाइट से भी फास्ट है, स्पीड ऑफ लाइट से भी फास्ट है। मतलब अगर मान लीजिए कि 2 क्यूबिट को हम एंटेंगल करते हैं तो ढेर सारे क्यूबिट को हमको एंटेंगल करना पड़ेगा। नेक्स्ट, आप इसको एंटेंगल मैथमेटिकल कोरिलेशन लेना पड़ेगा, क्योंकि हमको एल्गोरिथम लाना है ना, एल्गोरिथम से हमको रन करना है, क्योंकि जो भी आप प्रोग्रामिंग करेंगे उसका आंसर चाहिए ना। तो मैथमेटिकल कोरिलेशन कर रहे हैं हम यहाँ पे। क्यूबिट्स एक एंटेंगलमेंट, फिर क्यूबिट्स एक एंटेंगलमेंट। अभी मैं मैथमेटिकल इक्वेशन से डिराइव नहीं करूंगा, आपको मैं जस्ट नॉलेज दे रहा हूँ व्हाट डू मीन बाय क्वांटम कंप्यूटिंग। नेक्स्ट, ये जो है ना, ये क्वांटम कंप्यूटर का क्या है, डायग्राम है इतना सारा अरेंजमेंट चाहिए। व्हाई? बिकॉज़ इतना छोटे से चिप के अंदर सुपरपोजिशन मेंटेन होना है। मींस व्हाट? -273 डिग्री सेल्सियस मेंटेन टेम्परेचर, तभी जो भी एरर नहीं आएगा वो सुपरपोजिशंस पे रहेगा। जब इलेक्ट्रॉन सुपरपोजिशंस पे रहेंगे ना, उसको एंटेंगलमेंट, एक क्यूबिट का एक क्यूबिट को एंटेंगलमेंट करना पड़ेगा, उसके बाद एक एल्गोरिथम रन करना पड़ेगा, उसके बाद हम मैथमेटिकल इक्वेशन है उसको सॉल्व कर सकते हैं। अब देखिए उसको कैसे बताइए, मैं बताता हूं। अब देखिए क्रिप्टोग्राफी, क्रिप्टोग्राफी में क्या है, यू नो तो आपकी कॉम्बिनेशन कितना है, क्रिप्टोग्राफी में कॉम्बिनेशन कितना है। अब देखिए अगर मोबाइल, अगर कोई 5 सेकंड में हैक करता है तो क्वांटम कंप्यूटिंग से कॉम्बिनेशन इतना बढ़ेगा कि उसको हैक करने के लिए 1000 करोड़ चाहिए। आप पासवर्ड रखते होंगे ना, पासवर्ड ए टू जेड ही रखते हैं ना, एक बाउंड्री है इंग्लिश का बाउंड्री, जो कीवर्ड में है, जो कीवर्ड है ना उसके अंदर में जितने भी अल्फाबेट है उसी के अंदर पासवर्ड रखेंगे। लेकिन क्वांटम कंप्यूटिंग क्या करेगा, वो ऐसा एल्गोरिथम बनाएगा, समझो वो एट ए टाइम सभी पॉसिबल कॉम्बिनेशन को लिख के हैक कर देगा। क्या क्या टाइगर रख सकते हो पासवर्ड, एलिफेंट रख सकते हो, कुछ भी रख सकते हो, लेकिन क्वांटम कंप्यूटर का जो है वो इतना फास्ट है और उसको पता है कि ये जो कीबोर्ड है इसी के अंदर ही सब कुछ है। तो 0 1 से सभी पॉसिबल जितने भी नाम है, जितने भी 1 2 3 है, सब कुछ करके आपका लैपटॉप हैक कर लेगा। तो क्या इन फ्यूचर में इसलिए सभी कंट्री वरी है। क्यों वरी है, मान लीजिए अगर हमारा डेटा किसी के हाथ में जाता है तो बहुत कुछ हो सकता है। एरोप्लेन जा रहा है, एरोप्लेन का टाइमिंग चेंज कर दे तो क्रैश हो सकता है। ट्रेन जा रहा है, ट्रेन का टाइमिंग डिजिटली तो है, अगर कोई हैक टाइमिंग चेंज कर दे तो एक ट्रेन को एक्सीडेंट हो सकता है। कोई बहुत अंबानी जैसे करोड़पति है, उसका अकाउंट में हैक हो जाएगा। तो इसीलिए इन फ्यूचर इसके ऊपर फंडिंग ज्यादा है, चाइना, अमेरिका, यूएसए इसके ऊपर ज्यादा फंडिंग। लेकिन देखिए अभी क्वांटम कंप्यूटिंग पब्लिक में नहीं है। सभी बोल रहे हैं कि क्वांटम कंप्यूटिंग हमने बना लिया है, लेकिन वो पब्लिकली वर्क ओपन नहीं कर रहे हैं। क्यों नहीं कर रहे हैं, बहुत बड़ा सिक्योरिटी है उसके लिए। अभी रिसेंटली वेंकट सुब्रमण्यम बोल के जो साइंटिस्ट क्वांटम कंप्यूटिंग बना है, वो मेरे कोलैबोरेटर है। 6-7 लोगों साइंटिस्ट को बुलाया गया था दिल्ली में, उसमें मैं भी था, मैं उनके साथ बात किया। तो ये क्या है, मतलब क्वांटम कंप्यूटर इतना शक्तिशाली क्यों है, क्योंकि क्वांटम कंप्यूटर के पास इतना शक्ति है कि वो किसी का भी अकाउंट हैक कर सकता है। अब नेक्स्ट गूगल इज क्लोजर देन टू अवर ब्रेक डोर। अब देखिए गूगल बोलता है कि मैंने 49 क्यूबिट का एक चिप बना लिया है। नेक्स्ट अब और एक गूगल क्लेम करता है क्वांटम कंप्यूटर प्रॉम्प्ट्स को 72 क्यूबिट प्रोसेसर। नेक्स्ट आईबीएम बोलता है कि मैंने एक ऐसा क्वांटम कंप्यूटिंग बनाया है जो 400 क्यूबिट है। नेक्स्ट वीडियो गेम, आपको पता है व्हाट डू मीन बाय सिमुलेशन। सिमुलेशन मतलब नेचर को कॉपी करना। जैसे कि आप ऐसे नेक्स्ट ले लो, जैसे कि आप वीडियो वीआर इफेक्ट देखते हो, तो हम उस दुनिया में पहुंच जाते हैं, लेकिन वो दुनिया एक्चुअली होता नहीं है। कुछ कंट्री क्या कर रहे हैं, एरोप्लेन चलाने चलाते हैं, लेकिन उसको लगता है कि सचमुच एरोप्लेन चला रहा है, लेकिन रियली में एरोप्लेन चलाना रिस्क है। अगर क्रैश हो गया तो करोड़ों का नुकसान होगा। जैसे चलाना है वो क्या सिमुलेशंस में चलाते हैं। नेक्स्ट मान लीजिए कि नेक्स्ट हम नेचर का कॉपी क्यों नहीं कर सकते, आगे आगे, क्योंकि जल्दी भी खत्म कर। हाँ बस देखिए एक कप चाय में, नेक्स्ट ले लो, 1 cup of tea contains 36 milligram of caffeine। caffeine और एक caffeine को हमको सिमुलेट करना है, एक मॉलिक्यूल ऑफ caffeine को हमको सिमुलेशन करने के लिए 10 to the power of 20 बिट्स चाहिए। 10 to the power 20 बिट्स चाहिए एक मॉलिक्यूल को सिमुलेशन करने के लिए। मतलब इतना सारा बिट्स, जो पूरा ब्रह्मांड में जितने भी ऑब्जेक्ट है उसको ऐड करोगे तो भी इतना नहीं हो पाएगा। मतलब हमको एक मॉलिक्यूल को सिमुलेशन करने के लिए जो हमारे पास जो लैपटॉप है उसके पास नहीं है, कैपेसिटी है, लेकिन वो कितना टाइम लेगा, 10,000 करोड़ साल लगेगा एक मॉलिक्यूल को सिमुलेशन करने के लिए। जो भी आप प्रोग्रामिंग करते हैं, प्रोग्रामिंग चलाते हैं ना, तो प्रोग्रामिंग चलते जाता है। हाँ, मतलब ये हमारा जो क्लासिकल कंप्यूटर है तो 1 0 पे चलता है, इसको अगर वही क्वांटम कंप्यूटिंग का जो क्यूबिट है 400 to 500 क्यूबिट का कैपेसिटी, वो जो है ना खाली 5 मिनट में सॉल्व करेगा। रिसेंटली ऊपर आइए, हाँ अपोजिट डायरेक्शन में लो, हाँ और ले लो क्योंकि जल्दी खत्म भी करना है। रिचर्ड फ्रीमैन, हाँ ये भी ले लो, हाँ ले लो बहुत जल्दी से। हाँ, चाइना लॉन्चेस द फर्स्ट क्वांटम कंप्यूटर। तो इसका मतलब क्या है? मतलब ये है कि अगर हम मान लीजिए मॉलिक्यूल सिमुलेशन करने में हम सक्सेस पा लिए तो हम एंटीवायरस बना सकते हैं। एंटीवायरस आजकल क्यों नहीं बन रहा है? क्योंकि वो छोटा है कि उसका बिहेवियर हमको पता नहीं चल पाता है। इट इज वेरी सेंसिटिव एंड इट इज वेरी, क्योंकि छोटे स्तर पे अगर हमको किसी भी चीज करना है तो बहुत मुश्किल है। आजकल वायरस जो है उसका बिहेवियर, डिफरेंशियल इक्वेशन, उसका रेट ऑफ चेंज क्या है, म्यूटेट होते रहता है। अगर हमारे पास एक ऐसा शक्तिशाली कंप्यूटर क्वांटम कंप्यूटिंग है तो दवाई की खोज में क्रांति आएगी। आजकल जितना एक्सपेरिमेंट चल रहा है दवाई को बनाने के लिए, कितना खर्चा चल रहा है और कितना सारा ढेर सारा टाइम वेस्ट हो रहा है, वो सब बच जाएगा। मान लीजिए हम एक इंसान का ब्रेन का सिमुलेशन करना चाहते हैं तो देख लीजिए कि हमको कितना क्यूबिट चाहिए। हमारे पास सब है लेकिन हमारे पास हमारे कंप्यूटर के पास वो कैपेसिटी नहीं है जिसको वो सिमुलेट कर सके। रिसेंटली जनवरी 105 का पूरा लास्ट में ले लो, भी मैं आइडिया देता हूँ, ये तो इसमें है, पूरा लास्ट में ले लो, और लास्ट में हाँ है, हाँ ऊपर ले लो जरा, ऊपर ऊपर और ऊपर, हाँ और ऊपर नहीं, और ऊपर और ऊपर और ऊपर, हाँ नीचे 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 और एक नीचे लो। हाँ, रिसेंटली गूगल ने कंप्यूटर उन्होंने एक अनाउंसमेंट किया, 105 को उन्होंने क्यूबिट्स बनाया। 105 का क्यूबिट्स का मतलब क्या है? ऊपर ऊपर ले लो, नहीं ऊपर, हाँ उस ऊपर, मतलब क्लासिकल कंप्यूटर को इतना साल लगेगा उसको सॉल्व करने के लिए। एक पजल है जो परम्यूटेशन कॉम्बिनेशन से बनता है, उस पजल को सॉल्व करने के लिए हमारे नॉर्मल कंप्यूटर को 10 to the power of 25 इयर्स लगेगा। लेकिन वही कंप्यूटर अगर हमारे पास क्वांटम कंप्यूटर से है, उन्होंने चेक किया है, अगर वही कंप्यूटर हम क्वांटम कंप्यूटिंग से हम करेंगे तो 5 मिनट में होगा। नेक्स्ट देखिए, ये है पब्लिकली है, सुंदर पिचाई का स्टेटमेंट नहीं पढ़ता हूं। इंट्रोड्यूसिंग बिलो अवर of the art quantum computing chip with a breakthrough that can reduce error exponentially as we scale up using more qubits. 30 years challenge in the field. 30 साल उनको काम लगा इसको बनाने में। In benchmark test, below what is standard computation in less than 5 मिनट, 5 मिनट में सॉल्व करेगा वो। That would take a super computer, जो सुपर कंप्यूटर है वो 10 to the power of 25 years लगेगा। ये सुंदर पिचाई का ऑफिशियल स्टेटमेंट है। जो बड़े बड़े लोग जो स्टेटमेंट देते हैं ना, बहुत सोच समझ के देना पड़ता है हमको। नेक्स्ट, ये जो साइन है ना, ये बिलो चिप का है, रिसेंटली जनवरी में वो लॉन्च किया गया चिप है। नेक्स्ट, ये ग्राफिकल है, ये आप नहीं समझ पाओगे, मैं कभी समझाता हूँ। नेक्स्ट, हाँ, व्हाट हैज द गूगल बिलो ट्रैक, तो क्या और एरर करेक्शन ब्रेक तो फिर माइलस्टोन। नेक्स्ट, और एक देखो, इंट्रोड्यूसिंग बिलो अवर न्यू स्टेट ऑफ द आर्ट कंप्यूटिंग ब्रेक, तो फिर वही बोले हैं। नेक्स्ट, एलोन मस्क के साथ उनका चैटिंग चल रहा है। नेक्स्ट, हाँ अभी देखिए ये पूरा डिटेल्स में मैं जाऊंगा, लेकिन इंपॉर्टेंट क्या है, कॉन्सेप्ट क्या है। अगर आप अपना फ्यूचर क्वांटम कंप्यूटिंग में बनाना चाहते हो तो ये एक नया क्रांति है, ये एक मल्टीडिसिप्लिनरी है। एक दिन में मैं सिर्फ आपको आइडिया दिया हूँ कि क्वांटम कंप्यूटिंग का आइडिया आया कहाँ से, क्या क्या काम हो रहा है, लेकिन इतना आसान नहीं है। कॉम्प्लिकेशन इक्वेशन सॉल्व करना पड़ेगा, एक्सपोनेंशियल वेव इक्वेशन सॉल्व करना पड़ेगा, बहुत सारे चैलेंजेस आएगा। तो 20 मिनट हो गए सर, नेक्स्ट टाइम अगर मैं कभी आऊंगा ना, टाइम लेके आऊंगा ना, तो 2-3 दिन अच्छा पढ़ाऊंगा मैं आपको, ठीक है। और आप लोगों का मैंने कुछ नंबर लिया है और मेरे कुछ YouTube चैनल्स हैं, वो उसका मैं आपका नंबर में खुद सेव करके आपको मैसेज करूंगा अपना चैनल, आप लोग सब्सक्राइब कर लीजिएगा ताकि आपको नेट सेट का और कुछ इंपॉर्टेंट मैं आपको भेज सकूं। इसलिए ठीक है मेरे पास, ठीक है, ठीक है।
Cool.